Good morning, students. In today's lecture, we will discuss the phase diagram of sulfur system, which is a one component system. So various phases that will be present in the phase diagram of sulfur system are rhombic sulfur, which is also known as alpha sulfur, monoclinic sulfur, which is also called as beta sulfur, sulfur vapor, and sulfur liquid. So in the solid form, the sulfur is existing in the two allotropic forms, which is alpha sulfur and beta sulfur, which is also known as rhombic sulfur and monoclinic sulfur. Along with that, there will be liquid phase and vapor phase. As the sulfur is showing the polymorphism, it will exist in two crystalline forms, which are in equilibrium with each other at 95.5 degrees Celsius. Such temperature is known as transition temperature, at which one crystalline form is transformed into another crystalline form. Now below this temperature, 95.5 degrees Celsius, sulfur will exist in the allotropic form of rhombic sulfur. Whereas above the 95.5 degrees Celsius, it will exist as monoclinic sulfur. Now, the maximum number of phases that can exist in equilibrium in a one component system can be obtained from the phase rule equation. Now this is the phase rule equation, putting C equal to 1 and minimum value of F, which is the degree of freedom, number of degrees of freedom, can be equal to 0, putting the minimum value of F, which is equal to 0, and C equal to 1, we can get the maximum number of phases that can be in equilibrium. So maximum number of phases that can exist in equilibrium will be equal to 3 by using this equation. So what we can say here, all the four phases, they can't coexist in equilibrium in case of the sulfur system. On substituting P equal to 4, if we put all the phases together in equilibrium, when P will be equal to 4 and C equal to 1 in phase rule equation, we will get the value of F equal to -1, which is meaningless. Number of degrees of freedom can't be negative. That's why all the four phases can't coexist in equilibrium in sulfur system. Now, the phase diagram of sulfur consists of various curves, areas, and triple points. There will be 6 stable curves, 4 metastable curves, 4 areas, 3 stable triple points, and 1 metastable triple point in phase diagram of sulfur. As we can see in the figure in this slide, we can see there are 6 stable curves. These are BO, BO, then OA, AE, OC. This one is OA, AE, OC, AC and CF. AC and CF. These all are stable curves in phase diagram of sulfur. Okay, these are the stable curves of phase diagram of sulfur. Now, if we talk about the metastable curve, the metastable curve will be represented by the dotted lines here, like here OG, OD, AD, and CD. These all four are metastable curves. The curves shown by solid lines, they are stable curves, whereas the curves shown by dotted lines, they are metastable curves. So stable curves are here BO, AO, AE, AC, OC and CF. These are the stable curves. Metastable curves are OG, OD, AD and CD. Now what about the triple points? Triple points, as we can see here, O, A and C. These are the stable triple points. Whereas one metastable triple point is D. This D metastable triple point is obtained by the intersection of metastable curves, which are OD, AD and CD. Now we will discuss each and every curve, point and areas one by one. So first we are discussing here the areas. First of all, in case of areas, the system will be bivariant. To locate any point in areas, both and temperature and pressure, they have to be fixed. Now each area represents the condition for stable existence of single phase. In each area there is only single phase is existing. As we can see from the phase rule, when putting P equal to 1 and C equal to 1, the number of degrees of freedom are 2. For the single phase, for one component system, we will see the areas are bivariant. The system is bivariant. We can independently vary both the temperature and pressure in areas, or you can say we have to fix both the temperature and pressure to locate any point in the areas. So number of degrees of freedom here are 2. System is bivariant in the areas. Now different areas are here. We can see here to the left of BOCF what we are having, rhombic sulfur. There is only rhombic sulfur in the area left to the BOCF. Now area below BOAE, we are having sulfur in the vapor form. Only sulfur vapor is existing here. To the right of FCAE, only liquid sulfur is existing, which is represented by SL. Now the area enclosed by OCA, in this area we will have monoclinic sulfur, which is represented by the symbol SM. Now coming to the curves, first curve is OB. This one is the OB curve. It is also known as sublimation curve of rhombic sulfur. Along this curve, two phases in equilibrium are rhombic sulfur and the vapor sulfur, sulfur in the form of vapor. So these two phases will be in equilibrium along this curve and the system will be univariant. Number of degrees of freedom will be 1. Now starting from the point O, the point O is the transition temperature of rhombic sulfur. At this temperature, rhombic sulfur converts to the monoclinic sulfur. There is an equilibrium between rhombic sulfur and monoclinic sulfur at this point. So starts from the point O, the transition temperature of SR, this curve ends at point B. Below B, vapor pressure of rhombic sulfur can't be measured. Below B, we can't measure the vapor pressure of the rhombic sulfur. That's why this curve is ending here. We are not being able to extend this curve more to the left side. Now, if heating is done rapidly, rhombic sulfur can be heated above the transition point O along OD. What we are saying here, on continuing this curve, we are getting a dotted curve OD, where OD is what? Metastable curve. So what we are saying, when we are heating rhombic sulfur rapidly, by rapidly heating, we are not getting the stage of conversion of rhombic sulfur to the monoclinic sulfur. We are getting a metastable stage at which we are having rhombic sulfur along OD. Under normal condition, this area is representing the monoclinic sulfur. But if we are heating very quickly, we can get a metastable state in which we are having rhombic sulfur along OD. Such type of metastable state can be regained by just disturbing the system a little. On slight disturbance, what will happen? It merges into the curve OA. Such type of metastable state are having very short lifetime of span. These can be merged into the sublimation curve of monoclinic sulfur just by the slight disturbance. So this state is obtained only on heating rapidly the rhombic sulfur. So OD is a what? It is a metastable vapor pressure curve of rhombic sulfur. On slight disturbance, this curve will merge into the curve OA, which is the vapor pressure curve of monoclinic sulfur. Now, two phases, next we are moving to the curve OA, which is the sublimation curve of monoclinic sulfur. Along this curve, two phases that will be in equilibrium are monoclinic sulfur and vapor sulfur, or you can say sulfur in the vapor form, and the system will be univariant. Starting from the point A is corresponding to the temperature 120 degrees Celsius, which is the melting point of monoclinic sulfur, and ends at point O, which is a transition point. Now, to study the variation of vapor pressure of solid sulfur, we can use the Clausius-Clapeyron equation here. According to this, dP by dt, that will be equal to delta H of sublimation divided by temperature into molar volume in the gas phase minus molar volume in the solid phase. Now here we are talking about this curve OA, where monoclinic sulfur is in equilibrium with the sulfur in the vapor form. So molar volume of this monoclinic sulfur will be very less as compared to the molar volume of sulfur in the vapor form. So this will be a positive, and this is also always positive. So dP by dt will be positive. That's why we are getting a positive slope in this curve. Now, except at point O, at any other point all along the curve, only two phases are in equilibrium, which are Sm and Sv. You can say monoclinic sulfur and vapor form of the sulfur, they will be in equilibrium along the curve OA. If monoclinic sulfur is rapidly cooled, if this monoclinic sulfur is rapidly cooled, then rhombic sulfur may not appear at point O. The condition will not be normal. We are not getting the rhombic sulfur at point O. This curve will be continued to the OG, which is a metastable vapor pressure curve of monoclinic sulfur. In that case, we will get supercooled monoclinic sulfur. If monoclinic sulfur is rapidly cooled, then rhombic sulfur will not be obtained. We are getting supercooled monoclinic sulfur. That will be a metastable state. So curve OG is representing what? It is representing the metastable equilibrium between Sm and Sv. Now next one is the curve AE, which is the vapor pressure curve of liquid sulfur. Along this curve, two phases in equilibrium are Sl and Sv. Sulfur in the liquid form and sulfur in the vapor form, and the system will be univariant. Starting from the point A, which is the melting point of monoclinic sulfur, and ending at point E, which is the critical point beyond which only sulfur exists in the vapor form. Now for fixed temperature, pressure is automatically fixed along the curve. The system will be univariant and degree of freedom will be 1. The variation of vapor pressure of liquid sulfur with temperature can also be studied by Clausius-Clapeyron equation. Again, we are applying here. In this case, the equilibrium is in between the liquid sulfur and the vapor sulfur. So again, in this case, dP by dt will be positive, and we will get a positive slope for the AE curve. Now on supercooling the liquid sulfur, the curve AD is obtained. The same thing is here. Now we are cooling the liquid sulfur quickly. On supercooling, what will happen? The curve AD is obtained. Without getting this curve, we are getting this curve. So we are getting the metastable state, curve AD representing the metastable vaporization curve of liquid sulfur. It will represent the equilibrium between supercooled liquid sulfur and the vapor sulfur. Next one is curve OC. Curve OC is what? It is a transition curve. It represents the equilibrium between rhombic sulfur and monoclinic sulfur. It gives the effect of pressure on transition temperature of rhombic sulfur. The slope of OC curve is away from the vertical p-axis indicates that the transition temperature is increasing with increase of pressure. As we are increasing the pressure, the temperature is also increasing. From this line we can see, as we are increasing the pressure, the temperature is also increasing corresponding to this line, which suggests that the transition temperature is increasing with increase in pressure. Now this curve ends at point C, after which no monoclinic sulfur exists. Monoclinic sulfur disappears after point C. Now, effect of pressure on transition temperature can be explained by using Clausius-Clapeyron equation. Again, in this case, dP by dt will be equal to enthalpy change of transition divided by transition temperature into molar volume of the monoclinic sulfur minus molar volume of the rhombic sulfur. Now, as the density of monoclinic sulfur is less than that of rhombic sulfur, so its molar volume will be higher than that of rhombic sulfur. So Vb minus Va will be positive. And enthalpy of transition is always positive. So dP by dt comes out to be positive and its slope is positive. That's why increase of pressure will increase the transition temperature. Next one is the AC. Curve AC, it is the melting point curve of monoclinic sulfur. Along this curve, two phases in equilibrium are monoclinic sulfur and liquid sulfur. It gives the effect of pressure on melting point of monoclinic sulfur. Curve is inclined away from the pressure axis, showing that melting point is raised by the rise of pressure. As we are increasing the temperature is also increased. So we are seeing here melting point is raised by the rise of pressure. The system is again univariant. The rise of melting point with rise of pressure can again explained by the Clapeyron equation, from which we can see molar volume of liquid is greater than molar volume of solid always. So this will be positive. Enthalpy of fusion is always positive. So dP by dt will comes out to be positive. Next one is CF. CF is the melting point curve of rhombic sulfur. Here is the rhombic sulfur, here is the liquid sulfur. So this curve is representing the equilibrium between rhombic sulfur and liquid sulfur. Now, if liquid sulfur will be cooled at a pressure higher than 1290 atmosphere, above this pressure along this curve, if liquid sulfur will be cooled, we will get the rhombic sulfur. Then rhombic sulfur would crystallize at once. No monoclinic sulfur will be formed. Here we should write here rhombic sulfur not metastable. This curve representing the equilibrium between rhombic sulfur and liquid sulfur. Now curve CD, which is the metastable curve. It is the metastable melting point curve of rhombic sulfur. This curve represents the equilibrium between metastable rhombic sulfur and liquid sulfur. Again, by continuing this curve, we are getting this metastable curve, which is the CD curve. Along this curve, equilibrium will be in between metastable rhombic sulfur and liquid sulfur. Beyond point C, above this, the curve CD is becoming a stable melting point curve, CF of the rhombic sulfur. So this is a metastable melting point curve and this is the normal melting point curve of rhombic sulfur. Now different type of triple points we are obtaining on the phase diagram. The first one is the point O. Point O is corresponding to the transition temperature 95.5 degrees Celsius. At this point, the three phases in equilibrium are rhombic sulfur, monoclinic sulfur and sulfur in the vapor form. So Sr, Sm and Sv will be in equilibrium at this point and system will be invariant as degree of freedom is equal to 0. Point A corresponding to the temperature 120 degrees Celsius. At this point, three phases in equilibrium are monoclinic sulfur, liquid sulfur and vapor sulfur. So we can write it as Sm will be in equilibrium with Sl in equilibrium with Sv. Point C. Point C corresponds to the temperature 155 degrees Celsius. At this point, three phases in equilibrium are rhombic sulfur, monoclinic sulfur and liquid sulfur. So we can write Sr will be in equilibrium with Sm will be in equilibrium with Sl. Again the point will be invariant. Now from the phase rule we can see at triple points the degree of freedom will be 0. Now there is one metastable triple point which is the point D corresponding to the temperature 114 degrees Celsius. At this point we are having three metastable phases in equilibrium which are rhombic, liquid and vapor. This is obtained by continuing these curves. Along this curve, three phases in equilibrium are rhombic, liquid and vapor. As you can see this point, on this side we are having rhombic, on this side we are having liquid and on this side we are having vapor. So rhombic, liquid and vapor, these three phases will be in equilibrium along this metastable triple point D. So this is all about sulfur system. In the next lecture we will continue with the two component system.